In this video, we're going to derive the Navier-Stokes equation. So, recall that the Navier-Stokes equation is a statement of the conservation of linear momentum. So basically, force is equal to mass times acceleration. And so we are going to say that we have a differential mass element which we'll call dm. And for that mass element, we can then write Newton's second law as delta F is equal to delta M times the material derivative of the velocity of that particle, or of that mass element. And we can rewrite that material derivative as U del V by del X plus V del V by del Y plus W del V by del Z plus del V by del T. So here we're covering both the local acceleration here as well as the convective acceleration here. So these are the two different types of accelerations that particle can experience. So we're going to pay attention to the left-hand side of this equation first. So we want to consider the forces that are acting on this little element. And this element has a mass, as I said before, of delta M and a volume of delta V is equal to delta X, delta Y times delta Z. So there are two types of forces that this little element may experience. The first type of forces is body forces. And in particular, we are considering gravity as the only body force that this element will experience. So the differential body force delta F sub B is equal to delta M times gravity. And we can rewrite that in component form as delta F B X, which is just going to be equal to delta M, the mass of that element, times gravity in the x direction. Similarly for the y component, delta M times gy. And similarly for the z component. So we have delta M times gz. So those are the body forces. The other type of forces that may act on our little element are surface forces. Now, surface forces can include two different types of forces. So this can include normal forces. And the normal forces that we'll have here are pressure. So we'll have basically pressure stresses, sigma, and then we'll also have tangential stresses, which will be forces when multiplied by the area, and those are shear. So those will be indicated by tau. And so we're going to draw some examples of what these forces look like here. To do this, we're going to draw our little element, our little mass element, and just consider the x components of these forces. Okay. So, given our coordinate system here with x to the right z coming out of the page, and y increasing upwards, we're going to draw our little fluid element here as a cube, or something approximating a cube. So here's our little cube, which has sides of delta x, length of delta x, delta y, I'll do a little bit higher up here, delta y, and delta z. So the volume here is just delta x times delta y times delta z. And now we can start to draw the stresses, or multiplied by the areas, that will act on our little element here. And here these stresses are all acting at the center, and we're going to use the first term of a Taylor series expansion to basically describe the stresses on the surface. So we'll start with the normal stresses here. So we'll draw this one right here. This is going to be sigma xx plus del sigma xx by del x, which describes sigma xx describes the that stress at the center of this cube, and then this del sigma xx by del x term describes how that stress is changing in the x direction, and we're multiplying that by delta x over 2, which is the distance from the center to that face. So it's given some incremental change over that distance, and then we multiply that by delta y delta z, which is the area of this right-hand face. So we basically have a stress here multiplied by an area, which gives us a force. So that's on the right-hand face. Now on the left-hand face, we'll have something similar. We will have sigma xx minus del sigma xx by del x. Again, times delta x over 2, the distance from the center to the left-hand face, times delta y delta z, which is the area of that face. And so these are the two pressure forces acting in the x direction. Now, we can then move on to surface forces. So for surface forces, we will have surface forces in the x direction acting on the top face and on the bottom face. And then we'll also have surface forces acting on the front face here and on the back face. So we have 4 surface forces acting on this little cube. So this first one here on the top is given by tau y sub x. So here the subscript y indicates that it's on the y face, which means the top or the bottom face, and x indicates the direction of the stress. So tau y sub x tells us that the stress is on the top face acting in the x direction. So plus del of tau yx by del y. So this is again the stress at the center of the cube plus the gradient of that stress multiplied by some distance across which is acting, which is delta y over 2, the distance from the center to the top face, multiplied now by the area of that top face, which is delta x delta z. And we can do something similar for the bottom one right here. This one will be tau yx minus del tau yx by del x. That's by del y, multiplied by delta y over 2, and multiplied by the area of that bottom face, which is delta x times delta z. So that covers the top face and the bottom face. Now let's do the one on the front face right here. So this is going to be tau of zx. So it's on the z face and it's pointing in the x direction, plus del of tau zx by del of z times delta z over 2 times delta x delta y. Again, that's the area of that face. And finally, for the back face, we'll draw this right here. This will be tau of zx minus del of tau zx by del z times delta z over 2. And this is multiplied by the area of that face, which is delta x times delta y. So these are our 6 different surface forces that are acting in the x direction. You'll note I haven't driven or haven't written down or drawn the gravity force because it's presumably acting in the y direction, the negative y direction. So just to make a note here about what these stresses represent. Here, and I said this before, the stresses, which are sigma xx, tau of yx, and tau of zx, are at the center of this cube. And what we're doing is, we're using the first term of a Taylor series expansion to describe the stresses on the surfaces. And then, of course, we multiply that expression for those expressions for stress by the surface area to give us the force. Okay, so we have these 6 different surface forces. We want to add all of those together and to find a sum or a net force, a net surface force in the x direction. To do that, we end up with the following expression. So the net surface force in the x direction is then, and we'll call this delta f sub sx. So this becomes del of sigma xx by del x plus del of tau yx by del y plus del of tau zx by del z multiplied by the volume of the cube, delta x, delta y, delta z. And if you go through and work this out, you'll see that, for example, when you're adding together, say this term, this pressure term and this term, you'll find that this term cancels with this term, and et cetera, on for these other terms as well. And so you end up with simply this expression that we have here. So those are your surface tension forces. We haven't included our body forces yet. If we include gravity as our body force, then the net x force is going to be delta fx is equal to, and here we're just adding together body forces and surface forces. So this will just become rho of gx plus del of sigma xx by del x plus del of tau yx by del y plus del of tau zx by del z multiplied by delta x, delta y, delta z. So here's our gravity term right here, and our surface terms are there as well. Okay, so this is all for just the x direction. We can do something similar for the y and z directions to find the net forces in the y and z directions. We're not going to go through this in detail, but I'll write the final results. So our differential net force in the y direction is going to be rho gy plus del of tau xy by del x plus del of sigma yy by del y plus del of tau zy by del z, again multiplied by the volume delta x, delta y, delta z, and the differential net force in the z direction equal to rho gz plus del tau of xz by del x plus del of tau yz by del y plus del of sigma zz by del z. And this is all, again, multiplied by delta x, delta y, delta z. And so again, with these terms, we have shear stress terms here, 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 and here. And we have pressure terms here and here. So these represent, the pressure terms represent the pressure on the y face and on the z face. And the shear stress terms represent shear on the different faces as well. So now we have the full expressions for all of our forces in the x, y, and z directions. And so now we can take those and we can substitute those back into our momentum equation, our conservation of linear momentum equation. Okay, so when we do this, we end up with rho gx plus del sigma xx by del x plus del of tau yx by del y plus del of tau zx by del z is equal to rho times u, so here's our acceleration term, del u by del x plus v del u by del y plus w del u by del z plus our local acceleration del u by del t. So that's our x component of the conservation of linear momentum. Our y component here is rho gy plus del of tau xy by del x plus del of sigma yy by del y plus del of tau zy by del z is equal to rho, again, times our acceleration, u times del v by del x plus v del v by del y plus w del v by del z plus del v by del t. That's our y component. And our z component is similar, so we have rho gz plus del of tau xz by del x plus del of tau yz by del y plus del of sigma zz by del z is equal to rho times u times del w by del x plus v del w by del y plus w del w by del z plus del w by del t. And hopefully you see that pattern emerging. So in each case, for each component, we have our gravity term first. We have all the force terms on the left-hand side are gravity, our surface forces, and then on the right-hand side, we have essentially mass times acceleration. Now, these are our three components, our three equations describing the conservation of linear momentum, but there is kind of a problem here in that if you count up the number of unknowns and then the number of equations, you'll see that we have quite a mismatch. So we have more unknowns. So how many unknowns do we have? If we include density as an unknown, we have 13 unknowns. So we have u, v, w, and then we have all our sigmas and all of our taus. So we have 13 unknowns, and we only have 3 equations here. And if you count continuity, then we have 4. We have to somehow have more equations or relate these terms to other terms in order to try to solve this. And so what we can do is that what we need to do is we need to define some expressions for the stresses in terms of velocity and pressure fields. And we've seen something like this before. If you'll recall from earlier in the class, we defined that tau, and this was tau sub yx, although we didn't say it at the time. This is equal to mu times du by dy. And this was for a 1D Newtonian fluid or flow. And so for a 3D flow, we can come up with similar expressions, or the full expression here, and write the shear stresses down in terms of gradients of the velocities. So for 3D flow, the shear stresses are as follows. So we have tau sub yx is equal to tau sub xy, it turns out, they're the same, is equal to mu times del u by del y plus del v by del x. We can similarly write down that tau of yz, which is equal to tau of zy, is equal to mu times del v by del z plus del w by del y. And tau sub xz is equal to tau of zx is equal to mu times del w by del x plus del u by del z. So there we have 3 more equations for the shear stresses, and these relate to both tau yx and tau xy, so that sort of doubles the number of equations. And we also have similar expressions for writing down the normal stresses. And this is for incompressible flow. So we have sigma xx is equal to minus the pressure plus 2 mu del u by del x. Sigma yy is equal to minus p plus 2 mu del v by del y. And sigma zz is equal to minus p plus 2 mu times del w by del z. And I'll just make a note here that P is pressure. So, we're not going to go through the details of how we plug these in and simplify, but as long as we assume that we do in fact have incompressible flow, which means that the density of the fluid does not change, so rho is a constant, and also assuming constant viscosity, so Newtonian flow, then we get the full Navier-Stokes equations. So here we're writing down the acceleration term on the left-hand side this time. So rho times del u by del t plus u del u by del x plus v del del u by del y plus w del u by del z is equal to rho gx minus del p by del x, so that's the gradient of the pressure, plus, and here we have our viscosity mu times del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared. So that's the x component. The y component is similar, so rho times del v by del t plus u del v by del x plus v del v by del y plus w del v by del z is equal to rho gy minus del p by del y plus mu del squared v by del x squared plus del squared v by del y squared plus del squared v by del z squared. And finally, we have the z component, rho times del w by del t plus u del w by del x plus v del w by del y plus w del w by del z is equal to rho gz, the gravity component in the z direction, minus del p by del z, pressure gradient in the z direction, plus mu times del squared w by del x squared plus del squared w by del y squared plus del squared w by del z squared. So those are the Navier-Stokes equations. We have x, y, and z components here. And again, the left-hand side basically represents material acceleration of a fluid at a point. So that's your mass times acceleration, essentially. You have a body force here, which is your gravity. You have a pressure gradient right here. And over here you have, this whole term represents the effects of viscosity. And so in combination with continuity, those equations provide a complete description of incompressible Newtonian flow, and therefore they're called the governing equations of a flow, or fluid mechanics.